of mathematics, I can say. His research area is MHD, dispersion, stretching sheet problems, and convection problems. He has done many courses in NPTEL. Even he has done some art-related course also in NPTEL. He started his career as a professor from MSRIT. Then he went to National College Basavangudi. Then he worked in RVCE. Then he has guided 6 students already, and presently he is guiding 6 students. He has worked with VTU in various positions, like he was chief superintendent of exams, he was in board of studies, he was in board of examinations, so many in VTU as well as in autonomous institution. Even he was BOE for Alliance University also. He was the paper reviewer he is the paper reviewer for many journals, and he is the external examiner currently also for PhD students. He was on editorial board for so many journals, and he has organized many international conferences and quite a few national conferences, I can say. He is the member of many professional bodies. He has published more than 35 papers. He has published in international journals. He has published around 20 papers in national journals. So I think he is the right person to be. Means I asked him whether shall I conduct one. He's the force behind this FDP, I can say. So driving force, I mean. So I'll hand over the session to you, sir. Sorry I could not introduce you in full because of the shortage of time.
Thank you.
Okay, sir. Over to
Thank
you.
you.
Okay.
Thank you, Sripad, for a nice introduction. So you've given good words about me. I don't know how far I deserve that. So whatever you said, I don't know. So people will finally come to the conclusion that whether I deserve it or not. So now I can share the presentation now.
Yeah.
You're given that rights.
Yeah.
Your entire screen. Okay.
Present now window. Present now window.
Are you able to see the?
Yes, sir. Yes, sir.
Yes. At the outset, good morning to everyone. At the outset, I'm grateful to management of SAPTHAGIRI College of Engineering, in particularly Professor Sripad Markande and his team, for giving an opportunity to present my work before you people. So I have taken the general topic, not a particular case. At the end, I would like to present some of the important things, what I have done so far. Even Sripad Markande and myself together worked on these different models, so dispersion models. So I have taken the rectangular channel flows, and he was taken the cylindrical flow, the flow in the cylinders. So that is a tube flow. Here main things are mathematical modeling of dispersion in fluid flows. See, mathematical modeling is a very important concept. It plays a vital role in our day-to-day life. Whatever may be the given physical situation, we can give a mathematical structure in terms of equations. And these equations may be algebraic equations or differential equations. So here the main important thing is mathematical modeling. It plays a vital role. So this is a mathematical modeling. Mathematical modeling is very important. You take any situation, we can give the mathematical structure. Simple example, if we take the traffic flow, there is a problem, traffic jam is there, how to sort out that problem. So we can assign different variables, there are too many unknowns, and finally we can give a mathematical structure in terms of equations. Those equations may be algebraic equations. Just now you have seen that using different techniques how to solve the system of equations. Professor Manishankar was explaining the different methods of solving system of equations using Gauss-Seidel iteration method, etc. Using those methods, we can solve the system of equations. But you have to make certain assumptions. If you take all the unknowns into the consideration, that becomes very difficult to solve the system of equations. If there are too many unknowns, how to solve them? That becomes a great challenge for us. Now what you have to do is you have to minimize, you have to make certain assumptions and minimize the number of unknowns, and we can give a mathematical structure in terms of equations, algebraic equations, and we can solve how to control the traffic flow in particular signal. So that is a mathematical modeling. And now the present scenario is we are suffering with, or there is a pandemic situation everywhere. So COVID-19. For that also we can give the mathematical structure, we can make the mathematical modeling, and we can solve that problem. That's how it is increasing, that so epidemic is how it is increasing everywhere. And what is happening, we can give the mathematical structure to that physical situation. That's the most important thing is you take any situation, any problem, for engineers especially, it is the most important thing, mathematical modeling. Whatever they do, first they will give a mathematical structure to the physical situation. That's the most important thing for the engineers. You take any problem, engineering problem, first is the mathematical modeling. Then we can discuss that using the different techniques. So here I'm going to give the mathematical modeling for the dispersion. So much is there in dispersion also, it is an ocean, but we are considering a little bit of it, a drop of it. So dispersion in fluid flows. So dispersion of a solute, how it is going to disperse in the fluid flow, that we are going to discuss in my study. So this is about the dispersion, mathematical modeling of dispersion in fluid flows. So before going to the dispersion in fluid flows, there are two important terms that come across in our study, that is fundamental definitions of diffusion and dispersion. Always there is a confusion. What is the difference between the diffusion and the dispersion? So I still remember that. So once Sripad was explaining this, what is a diffusion in one of the presentations. Diffusion plays a vital role. What is the difference between the diffusion and dispersion? There is a confusion always. Some people say that, so diffusion is the net moment of anything, for example, atom, we can take ions and molecules, from a region of higher concentration to a region of lower concentration. And also we say diffusion is driven by a gradient in concentration. So in fact, the word diffusion derives from the Latin word diffudere, which means to spread. It is going to spread or scatter in the fluid, or in the fluid, that we can say. So these fundamental definitions in technical literature on dispersion pertaining to laminar flows, we are going to consider laminar flows. The terms dispersion and diffusion are not always used with clarity. So if you take the dictionary meaning of this, always dictionary meaning gives diffusion and dispersion in general use as synonyms for each other. So now we have to make a clarity in this diffusion dispersion. Dispersion and diffusion are usually prefixed with convective and molecular respectively. So here you can say, we say this a molecular diffusion and convective dispersion, so that more clarity will be there. That's the basic idea of these definitions. Definitions play a vital role in studying the dispersion models. Now, what is this diffusion? So basically, diffusion is a time-dependent process, very important thing. And what happens, it is spontaneous spreading of matter. It may be matter is a particles, matter. It may be heat or momentum. Now, it is a process by which molecules spread from where higher concentration to the lower concentration, area of lower concentration. And it's a gradual mixing. So we have to make the clarity with respect to diffusion and dispersion so that we can study the dispersion models, various models we can study. And one more thing is, so the dispersion, the diffusivity can be defined in the form mass transferred per unit area per unit time in fluid under unit concentration gradient. This is the main thing of the diffusivity. How to find out the diffusivity coefficient? For that, we use this definition. We try to find out the diffusivity coefficient. It's a most important thing. And what is the molecular diffusion? The molecular diffusion means the scattering of one fluid in another resulting from random molecular motion. And it is governed by the fixed law. Fixed law says flux is proportional to the concentration gradient. That is given by this important expression. This is called the empirical formula for the molecular diffusion. And various terms here are given. C is the concentration, Y is the distance in the specified direction, D is the coefficient of diffusion, and P is the rate at which the quantity is transported across a unit area normal to the direction Y. This is a most important result that quite often we use this. From this only we derive the important expression for the unsteady convective diffusion equation. Finally, that is the ultimate goal for us. Now this is about the, now what is the diffusion, what happens? So at different levels, what is going to happen that we are going to see in this particular figure. So this is at T is equal to 0, at T is equal, so we are taking a thin concentrated band. It is the, some solute is here. So at T is equal to T0, that is the time T is equal to 0. Now, when the time progresses, what happens? This is between, we can say 0 less than T up to infinity. We can take between the 0 and infinity. We can see it is molecular diffuses through the B. Another fluid is there. A is the thin band and B is the fluid. It is diffuses through the B. Now, after a long time, maybe we can say T is equal to infinity, long time. So after a long time, what happens when the T becomes infinity means it may be more time. After a long time, molecules of A are uniformly distributed along the tube. This is the tube we have taken. This is the most important thing. These are the things happening in diffusion. So dispersion is a form of mixing and act distributing one substance in the another. So this molecular diffusion and so convective dispersion. So it is called convective dispersion. In most of the things, what we say is diffusion plus convection becomes the dispersion. So what happens? There is a diffusion and also there is a motion. Convection is happening, so that becomes the dispersion. Now, basically, we are using two important conceptual representation of the dispersion. One is the hydrodynamics, the other one the time series analysis. Using these approaches, different approaches, these are called principal lines of development in mathematical modeling of dispersion. So these two play a vital role in modeling the dispersion of the hydrodynamics and the other one the time series analysis. So mainly we concentrate more on the time series analysis. Now diffusion dispersion coefficients, these are the basic fundamental results one can get from the literature. Units of the dispersion and the diffusion are one and the same that I've given here. And what is the diffusivity coefficient, which is very important in our study, and dispersion coefficient also very important. These are the some of the points noted here so that everything will be clear for you to solve a problem in dispersion of a fluid or dispersion of a solute in a fluid flow, taking the different modules. Now, in fact, there are infinite number of modules available in the literature. There are many. I have noted, I've taken down some of them. That is the Taylor's approach, Harris approach, Batten approach, Gill and Sankar-Subramanian approach. There are many approaches are there. So Taylor's gave a simple recipe of the calculation of conceptual dispersion in bounded shear flow at a large times after injection. Once the solute is injected, what happens after a long time, that is given in the Taylor's approach. This is a Taylor's approach. Now, what about this Harris approach? There are many approaches. So we are focusing only on the Gill and Sankar-Subramanian approach. Nowadays, we are using most of the researchers are concentrating on the Gill and Sankar-Subramanian approach. So in the Harris approach, there were certain lacuna in the Taylor's result. So Harris used the moment approach to generate Taylor's results to include the exact effect of axial molecular diffusion, which is quite significant if the Peclet number is very much less than 100. So if the Peclet number is less than or equal to 100, so we can use this Harris approach. So what is this? The Batten approach. It is a modified method of Harris approach, which is called statistical approach. So here also they use the moments and to find out the dispersion after a long time. So it is used for short and moderate times after the injection of solute into the flow. Now, most important thing for us is this Gill and Sankar-Subramanian approach. So this we are going to use in our study. So Gill and Sankar-Subramanian showed that an exact solution of the unsteady convective diffusion equation valid for all the times, maybe short time, moderate time, long time, and can be developed by using the series expansion originally proposed by Gill. So Gill has given this series method, series technique expansion. Using that, Gill and Sankar-Subramanian developed a method to find out there's a dispersion at different levels, short, moderate, and long times. So other than these three methods, Lytle approach is there, random walk approach, Smith delay diffusion method, finite difference method, finite element method, Batten-Stokes method, integral transfer method. So too many methods are there. For our problem also, we can use the finite difference method, what I learned in the previous lecture. So using that also we can solve what is called partial differential equation. Ultimately, we are going to solve the partial differential equation. We know that whenever you give a mathematical structure to problems, mathematical structure to physical situation, particularly fluid mechanics, we are going to get partial differential equations. Generally, it turns out to be a partial differential equation. How to solve the partial differential equation? That's a major challenge for us. So tackle that, we use different approaches. Sometimes in order to solve the partial differential equation, we use a method of separation of variables. Sometimes we use finite difference method, finite element method. All these techniques we can use to solve the partial differential equation. That is our ultimate goal. Now we have different, so what is the work done so far by the Taylor's Harris dispersion for particularly Newtonian fluids, because we focus more on Newtonian as well as the non-Newtonian fluids. So here we have the Taylor's used different approaches, Taylor series approach, Taylor's and Harris approach for Newtonian fluids. So this is a very important thing. These are the things they have used in learning the dispersion. Taylor's and even Erendon, Chatwin. So in the Erdogan and Chatwin, 1967, what they have done is they have examined the influence of small curvature on laminar dispersion and have shown that Taylor's results are true if the pipe is uniformly curved. So that is a restriction. If the uniformly curved, we can use this and we can get back to the Taylor's results. In the case of Gupta and Chatterjee, what they have done is, so following the Taylor's approach, have shown that the solute is dispersed relative to a plane moving with the mean speed of an electrically conducting fluid flow with an effective Taylor diffusion coefficient, which decreases with the increase in the strength of the magnetic field. So these are the different things. These are available in the literature. There is no need to go through these factors. I hope that you can follow this, go through this, you will come to know what are the things they have done in the case of Newtonian fluids, Taylor's approach in the case of Newtonian fluids. Apart from this, we have the non-Newtonian fluids. Mainly non-Newtonian fluids, where even we have considered couple stress, microflow fluids, Casson fluids. So these are the fluids we have considered in our study also. Nowadays, people are using viscoelastic fluids, and they are studying the dispersion for these fluids also. So this is about the non-Newtonian fluids so this Taylor's and Harris approach used. So now the major issue for us challenge is Gill-Shankar-Subramanian approach. This we are going to use. So in this case, what happens? So once you get the Gill-Shankar-Subramanian approach, and we can get the Taylor series result in the limiting of large Becquerel number, we can get back to Taylor's result from the Gill-Shankar-Subramanian approach. So this is a more general one. It's a more general procedure or the method or model, we can say. From that we can get the Taylor's as well as the Harris results. That's why this is a most general one, and this is a very important method that we are going to use in our study. And most of the people nowadays, they are using only GS model. This is called popularly known as GS model. So that's a Gill-Shankar-Subramanian model. So this is the convective equation we are going to get. So we are going to solve this equation, and we try to find out the different coefficients K1, K2, etc. that plays a vital role. We are going to input back to the physical situation. So Gill-Shankar-Subramanian people have studied, and so here Gill-Shankar-Subramanian has given the study. That's an unstudy. He has given, in fact, the solution to the convective diffusive equation. That's an exact solution to the given problem. It is not the approximate one, it is the exact solution, and we are making use of that solution to solve the problems in our study. Now, here most important and the thing is, Annapurna and Gupta were the first to investigate dispersion using the GS model, that is the Gill-Shankar-Subramanian model, in Newtonian electrically conducting fluids. That's the most important things. Newtonian electrically conducting fluids. They considered the shear flow of conducting fluid in the presence of magnetic field, and they have studied the dispersion here. So we can get all this information. Even so, Professor Sudeshwar and Moses, Indira, even we have Markandeya, including Markandeya and myself, we have studied the dispersion using the power law fluid, micropolar fluid, Casson fluid. So different fluids were used to study dispersion, not only in the channel flows, but also in the tubes. These are the things we have done. So in the dispersion. Now comparison of the different models, this is a very important thing. Dispersion model, convective equation, what happens to convective equation? Ultimately, we are going to solve this convective equation. So now here for a Taylor's, this axial diffusion is very much smaller than the transverse diffusion, so that we can neglect dou square C by dou x square. So the equation becomes very simple. We can solve this simple equation using various approaches, and we can interpret back what is that. So dispersion coefficient, what happens to the dispersion, that we can discuss solving this equation. Now in the case of Harris, both are important, that is axial diffusion as well as the transfer diffusion are very important in the case of Harris approach, and the convective equation becomes like this. This we can solve using different techniques, right? And in the GS model, the most important thing is, so we'll have this unstudied convective diffusion equation where we have both axial diffusion, transfer diffusion, and one more extra term is there. We are going to solve this equation using different techniques. Even we can use finite difference method, finite element method to solve the this partial differential equation. This is the partial differential equation we are going to solve, right? So these are the things we are saying about the dispersion, and I would like to solve a problem which is most important for the people to understand what is happening. That's important thing, right? I hope that you are getting some information, clarity about the diffusion and dispersion, and what are the different approaches, major dispersion models, that is the Taylor's model, Harris model, and Gill-Sankar-Subramanian model. These are the three important models are effectively used in the literature. And what happens to the convective equation and the different assumptions, and these are the equations you will get. You have to solve these equations to interpret back to the what is happening to the dispersion in the fluid flow, right? Now I would like to present one important problem, that is the effect of magnetic field on the three-dimensional flow, because we have two-dimensional dispersion, three-dimensional dispersion. Many people have worked on two-dimensional dispersion, and even in the three-dimensional dispersion. I have taken one problem on the three-dimensional dispersion, effect of magnetic field on the three-dimensional all-time dispersion, that is we are going to use the GS model, Gill and Sankar model, in a weak electrically conducting Newtonian fluid flow. So here it is a Newtonian fluid flow. For this we are applying the transverse magnetic field, and here you can see it is a rectangular channel. In this, the breadth is 2b, height is 2h, and we are going to introduce a source of solute, that is solute at z equals 0, and we are going to apply the magnetic field in this y direction, and we study. This is called the transverse magnetic field. Transverse field we are going to apply, and we study the dispersion. So here we are going to consider the electrically conducting and incompressible Newtonian fluid which flows in the rectangular duct due to the axial pressure gradient. The flow is due to axial pressure gradient, and so we are going to apply the transverse magnetic field, uniform magnetic field in the y direction. And then what happens, so even you can apply the magnetic field in the x direction also, it will have the similar effect, but we are considering y direction. So we are going to apply uniform magnetic field in the y direction. And here we make certain assumptions. Otherwise, the equation of motion becomes very complicated. Already Professor Manishankar has shown the different equation, that is a equation of continuity, equation of motion, equation of energy, all those things. Here we are going to consider, we are going to reduce the equation of motion into solvable form. How to do that? And here we make certain assumptions. What are the assumptions we do? We assume that the induced magnetic field produced by the motion of an electrically conducting fluid is negligible compared to, it's a very important thing, compared to the applied uniform magnetic field. So what happens because of this assumption is valid for a very small magnetic field, magnetic Reynolds number. What is the magnetic Reynolds number? Magnetic Reynolds number is Rm. You are going to represent that by Rm. So this Rm is very small. So this is the assumption we make. This assumption is valid for a very small magnetic Reynolds number Rm. And one more thing is, no external electric field is applied, and the effect of polarization of the ionized fluid is negligible. And that means to say that we are assuming that electric field E is equal to 0. There is no effect of this electric field. Now, making these assumptions, we are going to find out the velocity. So what are the components? So actually, so x component is 0. So this y is 0. So the z component is, it's a function of x and y. So this is a three-dimensional flow, and it becomes a function of x and y. It depends upon x as well as y direction, and this is, we are going to find out the velocity profile afterwards. Now, what are the governing equations for this fluid flow under these assumptions? So the basic equations are the first equation, the x, y, and this is the component, very important component that you have to write down. So now here we have taken only this. What about the magnetic induction equation? And it is clear that the magnetic induction equation as well as the magnetic boundary conditions are not needed for solving this equation, this partial differential equation. That is because we have assumed that this Rm is magnetic Reynolds number. Rm is very much small. So which enables us to neglect the induced magnetic field, and we get these equations. So to solve this equation and at the certain conditions, what are the conditions? Boundary conditions. The axial velocity u of x comma y vanishes on the inner walls of the rectangle duct due to the no slip condition, and that can be written as u is equal to 0 at x equals plus r minus b, y is equal to plus r minus h. Now we have to solve this partial differential equation. How to solve this partial differential equation? That's a very important thing. So what to do? How to solve this under these conditions? So it is not a so simple equation. It's a complicated expression. And what we do is we try to find the velocity profile. For that, we are going to make an important assumption. We are going to take u is equal to in the form of, so u is equal to, we assume this, u is equal to, we take the u in terms of uj, j is equal to 1. These things I have not given there. So we take the u in this form. Cos of beta j times y by h. So what is the criteria for taking u in this form? Here, if you take y is equal to h in the boundaries, so this is the solution of the linear partial differential equation. This partial differential equation is obtained by assuming a solution that satisfies the boundary conditions on any one of the walls. Here in this case, we are taking y is equal to plus r minus h, and we choose the vertical wall for this purpose. So we take u is equal to sigma I is equal to 1 to infinity uj cos beta j y by h. So this should satisfy on the vertical walls. If you take h is equal to y is equal to h, this becomes beta j. What is this beta j? That's also important for us. Beta j were taken, beta j is equal to, so 2i 2j plus 1 into pi by 2. Now if you take y is equal to h, this becomes cos of beta j. I is equal to 1 or I is equal to, you can start with I is equal to 0. You can start with I is equal to 0. When I is equal to 0, you get pi by 2. Pi by 2, cos pi by 2 is 0. So that this condition is satisfied. Because it is odd multiple of pi by 2, whenever we have cos of odd multiple of pi by 2, that becomes 0. So that this condition is satisfied. So we take u in this form and we substitute in this expression, and we get a ordinary differential equation which can be solved without any difficulty using the method of separation of variables. So once we make the substitution, we'll get a partial differential equation that we have to solve. That partial differential equation is very important for us. If you have that partial differential equation becomes an ordinary differential equation, here this u is a function of x only. Here we have taken u is a function of x, so that we will get a ordinary differential equation of the form d square uj by dx square minus beta j square by h square uj. So minus mu square sigma h naught square by mu f into ug. So that is nothing but 1 by mu f, so into dp by dz into h. So once you make this, if you take that uj is equal to so much in this differential equation, that partial differential equation becomes the ordinary differential equation. Using the separation of variables, we can solve this, and finally we'll get the velocity profile like this, in this form. So it looks very complicated, but it takes a lot of time to compute the velocity profile. It becomes a very lengthy process, but we have to do it. So in the three-dimensional case, the expressions will be very lengthy, so very tedious sometimes and laborious, but somehow you have to manage that. So velocity profile becomes a very lengthy expression, but easily we can compute the values. So this is about the velocity profile. Once you get the velocity profile, then what next? So taking this velocity profile, we have to find out so we have to make use of this unsteady convective diffuse equation. So now into this fully developed flow is introduced a cloud of concentration. This is a velocity profile. This is a fully developed flow. So we are going to introduce a cloud of concentration due to as instantaneous source at z equals 0. So in the figure I have shown that z equals 0, we are going to introduce a concentration, the transport of concentration distribution, in fact that is called C. C is a function of x, y, z and t. It depends upon time also. The rectangle that can be described by parabolic convective diffusion equation. This is a parabolic convective diffusion equation. So we'll get this equation. Here we have certain conditions. Under these conditions, we are going to solve this convective diffusive equation. So what are the conditions? Here we have delta of z. What is this delta of z? It is where delta of z is the Dirac delta function. It's a Dirac delta function. And what about the term phi of x comma y that specifies the source strength and the location? So now in writing these equations, so we have assumed that the channel is uniform. So here we have taken the channel is uniform, straight, and there is no material transport across the walls of the conduct, across the walls of the channel. So now the gradient at x equals 0, this gradient at x equals 0 must be 0 due to at x is equal to 0 it must be 0 because due to the symmetry. This is 0 and this is also 0 because of the symmetry. The fact that material never reaches, this is a very important equation, never reaches points where far removed from the source in the downstream is reflected in this expression. So limit z tends to infinity, that is a far removed points very far removed from the source. So it's reflected in this expression. This is limit z tends to 0, c and dou c by dou z is 0, that is given in this expression. Under these expressions, we are going to solve the equations. And mainly we'll focus on K1 and K2. What are these K1 and K2? How to get this K1, K2 values? So once this tedious process is there, you have to make use of so much of calculations, time you have to spend to get the values. There are limiting cases also. And here I have taken down only this mean concentration, average concentration of the mean concentration equation, and I solved this equation. I got K1 value and K2 value that I have given here. K1 is in fact U into F naught. So what is F naught? It's a big expression we get. And velocity profile already you know, that's also very lengthy expression. And you have to integrate and you have to evaluate that between minus b and plus b and also 0 to h, and you will get a K1 value. In fact, this K1 value is nothing but the average velocity. Once you calculate this, you'll come to know that it's average velocity. It's a big expression we get. So it will spend a lot of time. It's a very tedious calculation, and we get the K1 value. So here U1 U into F1 dx dy, that gives your K2 value. That is also very lengthy expression. So much of time you have to spend to learn the dispersion in the three-dimensional case. Three-dimensional is not so easy. If it is possible, we can make use of at this junction. We can use the finite element method or finite difference method to solve these equations, and getting K1, K2 values. That would be better, so that we can avoid so much of calculation and spending our time in getting the K1, K2 values. Now here I would like to discuss one important results and discussions, that is what happens when this magnetic field is applied to the dispersion. So here K1 is we call it as a convective term. The other one is here given clearly. Convective coefficient is K1. This is K1 is called the convective coefficient, and dispersion coefficient is K2. So in most of the cases, we try to figure out this K1 and K2. Once you get K1, K2, we can interpret back to the physical situation. So results and discussion, I have taken so many graphs are there. I'd like to throw light on this first one, so that we can understand the other things. So your K1 is, we have plotted K1 for various values of B by H. So here we can note that the K1 increase with the increase in the aspect ratio. This is called the aspect ratio. B by H is aspect ratio. If B by H is equal to 1, then what happens? That becomes the square. So this is the aspect ratio. Increases in aspect ratio from 1 to infinity. We have taken 1 to, so very large number. It can also be seen that the effect of magnetic field is to decrease the velocity gradient in the flow. M equals 0, there is no magnetic field effect. That is called a Newtonian flow. When M equals 1.1, so there is a decrease in the value. 2, it is still decreases. So that means the effect of magnetic field is to decrease the velocity gradient in the flow. That's the most important thing we can note from this. Like this, we have many other things to continue, and we have taken the different parameters to plot the graphs. And one more thing is here, the convective diffusive coefficient. This coefficient is nothing but the average velocity. So that only I given. So this is the velocity gradient in the flow. Okay. Now, so we have some more graphs. I've given more graphs on these different aspects, and it becomes very complicated for you people to understand. And what is needed is you should know how to solve the partial differential equation. Moreover that, so where can we use these dispersion models? What are the different applications? And we can use this in the biomechanics. Biomechanics plays a vital role. For example, if you consider the blood flow, and we are going to inject solute into the fluid flow. So how it is going to disperse in the fluid flow, that's very important thing for us to understand how it is going to disperse in the fluid flow. So we take that fluid flow, that's blood is there in the blood plasma, we take it as a Newtonian. With a suspension, that becomes a non-Newtonian. Now we are going to introduce some solute into that. Then what happens to that fluid flow, how it is going to disperse at various intervals, different levels, different times, and all those things we can study. And these are the different graphs I have taken more on this results. So mean concentration graph also are given. Too much is there to discuss, and I thought that the main important things can present it, so that one or two people can pick up these and they can do the work in this area, that is dispersion models. So there are certain unsolved problems. We can take here, we can take an uniform channel we have taken. So other regular cross sections we can take, elliptical, triangular, bent tubes. Same approach you can use, but you can take the different geometry and we can study the dispersion using the different models. You can use Taylor's, Harris, or Gill-Sanderson model, and we can study the dispersion in the other regular cross sections. Irregular cross sections, it becomes very complicated. One must be very competitive in solving the this partial differential equation. You may get a non-linear partial differential equation. How to solve them, how to tackle them is a great challenge for us. And so other is the solute mechanical, the anisotropic, then complex flow channels, irregular porous packing. Even we have studied the dispersion in the porous medium also, three-dimensional case. That's also very complicated expressions you will get, but it will have the similar effect that as the magnetic field. So porous medium effect will be as similar to the magnetic field effect, and we can study that also. So complex flow channels, irregular porous packing, wall reactions, heterogeneous and chemical reactions. There's interface mass transfer in the three-dimensional case. Also, we can study homogeneous bulk reactions. Too many problems are there available in the literature. So you can collect the information regarding these problems, and we can use this GS module to study the dispersion in various these problems. I thought that so I can present these problems so that one or two people you can pick up this, and we can work out, we can solve the problems using this GS model to understand the dispersion at various levels. So dispersion GS model gives the all-time analysis. This is called the all-time analysis, and we can make use of that model to solve these problems. These are some of the unsolved problems. And here I've given too many references. No need to worry about the references. And you can go through the references, too many I've given. I don't want to take a lot of time. I thought that I can give the overall idea about the dispersion model and one problem on the three-dimensional dispersion. So this is about the presentation. Sripad.
Hello, sir.
I don't want to take much of your time. I thought that I can give glimpse about the dispersion and the different models that are available in the literature, so that one or two people can pick up that and they can continue the research work in the different areas.
Really.
Is it okay?
Yeah, the session was wonderful session. So since we work together in the with these problems,
same area.
So the session was wonderful, sir. You gave all the introductories. You started from the beginning, and you ended with like a problem, and you have posed them different problems also, like irregular geometry is also there. Bent tubes still not done. Elliptical tubes, certain simple Newtonian case they have solved, but they have not considered non-Newtonian. So simple case, even professor from IISc has solved that. Ramchandra, A. Ramchandra Rao. But they have not considered non-Newtonian flows. So there are many problems, and as all of you know, dispersion need not be in tubes. See, in COVID situation, dispersion can be in air also. All those are problems for you. So many opportunities will be there if you are expertise in dispersion area.
That's why I started with the COVID situation only.
Yeah. That's what.
I told you, COVID.
So I will give 2 minutes for clarification of doubts, if any, to the participants. Participants, I give 2 minutes. You can ask the questions directly to the speaker. Or otherwise, you can post them in chat box. I will communicate to speaker and I will get the answer for you. So,
okay, then shall I conclude?
Yeah. Yes, sir. So
now our participants are also like our students. Even students are also not asking any questions in the classroom. So I don't know where they will be there. Even we are taking the online classes, and some of the students will be maybe sleeping. We don't know. That is the situation now in the pandemic. So it is happening. Okay, no problem. And so I am very grateful to
conclude in 2 ways, sir. They have followed each and
everything.
100% they have followed.
The conclusion you can give
in a
positive note. Yes, everything they understood. So I made it very clear. So that may be true. I don't know. So we should be always optimistic, right?
Yeah.
Right. So in a positive sense, it is
Yeah.
they've understood everything,
Yes.
and I take this opportunity to thank the principal, the management, the principal of SAPTHAGIRI College of Engineering, in particular Professor Dr. Sripad Markande, for giving an opportunity to present something in dispersion models, and also thank the organizers for the opportunity given to me, and also thankful to my management, BNMIT, management, director, additional director, principal, dean, all faculty for the opportunity. They're also there in this presentation. I don't know how far they have followed, because in our department, I'm in the dispersion. The others are in convection, stretching sheets, etc. So I don't know. So how it is dispersing in the field, I don't know. Our people have dispersed already, I don't know. So after
No.
hearing to dispersion,
People are there. They are listening to you. Yeah. They have not left. Hardly
okay,
one
no,
or two students have.
dispersed. Okay, dispersion,
Yeah.
employed, so dispersed. Right. Thank you. Thank you once again for the opportunity.
Yeah.
So I'm grateful to you people. Thank you, one and all.
Thank you, Dr. Manjunath. Your presentation was a very nice presentation. So I'll now ask since you have discussed dispersion problem, now it is the time to disperse. So we disperse for lunch session
Okay.
on online mode only. So we should rejoin at 2:30 today
Okay.
with the lecture from professor from University of Jamaica, University of West Indies, Jamaica. Right. So we shall meet at 2:30. Till then, I'll say goodbye.
Thank you. Thank you, one and all, once again. Bye bye. Bye
Bye.
bye.
Bye.